Hello, everyone. Welcome to the last class of our machine learning course. And before we begin, let me read you this SIGGRAPH policy against harassment. This live stream is moderated by ACM SIGGRAPH. We ask that all comments stay respectful of others and respect ACM's policy against harassment. This means to exercise consideration and respect in your speech and actions, and to refrain from demeaning, discriminatory, or harassing behavior in speech. Please be mindful of your fellow participants. All right, so welcome to class 7. And we will talk about reinforcement learning today, and I'll do a little bit of a recap. We have a guest, Andrew Glassner, who will be talking about reinforcement learning, and then we'll wrap up and tell you some tips on what to study further and where to go from here. And to work with Andrew's notebook, you can make a copy of the notebook that he has provided. And let's introduce our guest. Andrew Glassner needs no introduction. So he has been in the field of computer graphics for as long as I remember. And he has made significant contributions to both art and science in the computer graphics area. And he now works as a senior research scientist at Weta Digital. And recently, or a few years ago, he started getting into machine learning, and now he has a few books. So one of the latest books is out, and you can read about it, and I'll give you pointers on where to find the book. And it's available now. So let's bring in Andrew Glassner. Hi, Andrew. You are muted for some reason.
You muted me.
Not me. Now you're fine. So good. Okay. I can hear you now, and I think everybody can too. So very warm welcome to you, and thank you for taking the time to be here in our class. And just to start off, I think I did a small introduction, but I want to hear from you, your journey into computer graphics and then into machine learning, and what are you up to now?
So my journey, such as it is, it's more like a pinball bouncing around. I was thinking about it this morning because I've been watching these wonderful, by the way, thank you for doing this. Thank you for doing these sessions. This has just been a wonderful course, and I've enjoyed it very much. So since I knew you were going to ask that question, I was thinking about it. And my first brush with computer graphics that I can recall was when I was in 7th or 8th grade. Somehow I found a copy of a textbook that old timers will remember, Principles of Computer Graphics, I think it was called, by Newman and Sproul. And it was a black book with a white wire frame on the cover. And somehow I had a copy of this, and this was before the internet. So somewhere in the middle, there was a chapter on transformations. And I remember lying down in front of the fire at home with this book open and a pad to my right, trying to figure out what the heck a matrix is. And when you have two matrices together and these other numbers come out, what on earth is going on? And I remember sitting there with pencil and paper, like it was like a puzzle. You know, these things went in and this thing came out, and how did that happen? So then I went to Case Western Reserve University, where Fred Park was running a computer graphics lab that had a machine called the Evans and Sutherland LDS2. And the LDS2 was a very early, primarily a line drawing machine, but it had a raster graphics unit. And when I say unit, I mean a refrigerator. This machine was like 6 refrigerators side by side, and they were all hand wire wrapped, stacks and stacks and stacks of boards that had all been, connected up by hand. And there was the geometry unit, and then there was the wire drawing unit, and then there was the shading unit. And somehow I convinced Fred to let me into the lab in the evenings. And I used that system and learned some 3D computer graphics. Then after a year, let's just say I was not a very good student, and let's say I failed out
Well,
because it's
absolutely,
true.
yeah.
And then I needed to do something with my life. And at the time, the New York Institute of Technology Computer Graphics Lab, which had been started by Alvy Ray Smith and Ed Catmull, um, I knew of it. And it wasn't that far from where my parents lived. So I drove over and I just rang the doorbell. And someone stuck his head out. And I said, "Hi, I'd like a job." And it's like, "Well, who are you?" And I said, "I've got Polaroids." Because before I left New York Tech, I took pictures off our one screen. I took Polaroid pictures. See, I can make pictures. In any case, they gave me a job, and I worked there for a few years. And I realized how much I didn't know, and I really wanted to know it. So I convinced Case to let me back. I went back to Case, graduated as an engineer, almost changed majors. I actually left Case in the middle. After another year, I left to become a film major. And I actually had my film school schedule set up, and I had an apartment and a catalog and a phone number. And then I fell in love, and I couldn't leave my love. So I stayed in Cleveland and became an engineer and not a filmmaker. Although I became a filmmaker later, so go figure. Um, I went to graduate school at the University of North Carolina at Chapel Hill, where I had absolutely fantastic advisors: Henry Fuchs, Turner Whitted, Fred Brooks.
Oh my God,
Um,
those are amazing advisors
yeah,
to have.
I worked with and for them. That's how you learn computer graphics. That was pretty great. Um, and then I graduated with my doctorate. I went to um, I went to Xerox PARC. My plan was to become a teacher. And I always thought I'm going to become an academic. And I thought I'm going to take 3 years off and work in industry and then go become an academic. And after 3 years at PARC, first of all, I loved it. And second, it was one of those dips in the academic cycle. They
Mhm.
peak and they dip. And so the timing was wrong. So I stayed. And then I continued to stay. And then I went up to Microsoft Research in Seattle, where I was working with another fantastic group of people um, whom I could name, but I would leave someone out, and that would be a tragedy. But Jim Kajia was my manager, and that also was incredibly wonderful. My gosh, talking to Jim every day.
Yeah.
Um, did that for a few years, and then uh, went off on my own, and I did other things on my own. I went back to film school. In the interim, I directed some animation. I directed some internet game. I directed some live action. Wrote and directed some shorts. The film school thing. Um, Worked as a screenwriter briefly. Found that wasn't the world for me. And then a few years ago, I don't know, 5, 6 years ago, I was reading some articles on artificial intelligence, and it was the beginning of the deep learning revolution. And half of the articles were, "Oh my gosh, this is terrible. It's going to destroy civilization." And the other articles were, "This is the best thing ever. We're heading into a golden age." And I thought, well, what's the truth here? Are they both right? Are they both wrong? And being an engineer, I said, well, the way you learn is you learn what the thing is, and then you make the decision for yourself. So I learned deep learning and machine learning, and then deep learning, and found I was not super happy with the materials I was able to find, both on the web and in books. There are some very, very fine books, and websites and courses, but they didn't do it the way I wanted to do it. They didn't teach me the way I wanted to be taught. And when that happens, I think of other people who are like me, and I write a book for them. I write the book I wish I had. That's how all my books happen. So I did that, and then I was doing some deep learning for a while, consulting, and then I went to Weta Digital. And Weta is a visual effects company based in New Zealand that they made Avatar, Lord of the Rings, Planet of the Apes, Game of Thrones. Um, Absolutely, top end visual effects company, and they were keen on putting machine learning into their visual effects work. Um, and I was somebody who talked both computer graphics and machine learning, and and I had never worked in a film studio, and I thought it sounded fascinating. So I went there, and it is fascinating, and that's where I am now.
That's amazing. Actually, that's it's like you had brushes with so many people who are like legends in their own fields, and then you yourself, like I looked up to you. Like when I first came to SIGGRAPH, like in 1994, I like wanted to attend the class that you're teaching, the papers that you were writing, and they were like immensely accessible. So I want to thank you personally, actually,
Oh,
for getting me into the computer graphic field, and then making it very approachable and easier to understand.
you're very sweet. Thank you.
And so, similarly, I think I always ask my guests, like, what advice do they have for others entering the field? Because we've been in this field and things seem like second nature to us. But then, what should new entrants kind of focus on, and what's the essence of both computer graphics and machine learning that you think they could focus on and learn better?
Well, I always think of there's a problem with asking me what's the right way to go, because I have survivor bias. It I survived. I did all right. And so I look back on it and I go, well, that's the way to go. But that's not the way to go.
Right.
Everyone's journey is different. And by looking at the journeys of other people who have what I define as success, and success is when you're happy. That's success. And then whatever goes into making you happy, and happy to do what you do, and happy to work with who you work with and what you do, that's success. It's not title, it's not paycheck, it's not even so much what you're doing. It's, do you have that inside? Are you happy?
Right.
So what I notice is amongst the people I've observed who are happy, um, in terms of work, that there are three things going on. The first is that they know themselves. They know what they like. They know what they enjoy. And if possible, they find work that they enjoy. That's not always possible. And often you have to enjoy the work you're given. But there's almost always something good to be found in any work. If the work is useful to others in some way, then you find that and you latch onto that and you say, how can I be of the best service? And that's interesting, and that's a compelling thing to do.
No, that's
So
great advice, actually. Yeah.
so focus on the stuff that you love, and if you can't do what you love what you do. And if you hate it, don't do it. Find something else. The second thing is you do want to know your fundamentals, because you want to be able to do your work well. And so it's not enough to do well enough to skate by. You really want to know the stuff inside and out, because that's when you're able to really contribute new things. The more tools you have, the more diverse your contribution can be, and the more useful it can be, because you're not limited by the tools you have, which is why you got to keep learning. Learn whatever turns you on. Right now, I'm studying quantum computing because, I don't know, is it going to be useful next year? No, but it's fascinating. So yeah, let's learn that. And the third thing is connecting with other humans and other people and dogs. I'm a big dogs fan. So anything that's alive, it could be a basil plant that you love. That's okay. Connect with other loving, living things, because that keeps you both focused and energized. And if they're in your field doing whatever you're doing, then you get to stand on their shoulders. You get the benefit, just of a casual chat, and someone says, oh, but you could flip that. You could do the thing with the other way. I never thought of that. Oh my gosh, that opens up. Thank you. And how did that happen? Because you had some kind of a relationship with someone where you trusted them enough for you to tell your ideas, and they trusted you enough
Right.
to share. And I guess that's a small side note since we're on that.
Right.
Don't be precious about your ideas. Ideas are our currency as researchers. Once you've got the idea, then the rest is typing to to an approximation. But share your ideas. Share them with the best people you can find because they'll make them better. And then two things happen. One, you have a better idea. Two, you have a new friend and a collaborator. And that's good. Publish papers with other people. Um, so I would say, from what I've observed,
Mhm.
those are good things to do.
Right. No, I think that's great advice. So, and then also you talked about like connecting with people and sharing ideas, and I've seen you at almost every SIGGRAPH there. Could you talk a little bit about just giving back to the community that you share with, and your service to SIGGRAPH and other places?
Yeah, give back, give back, give back. I mean, we're all here because someone gave back.
Mhm.
We're all here because we read a book that someone wrote. Why do people write books? I will tell you, it's not for the money. People write books for love. They write books because they say, I want the next person to avoid the problems I had and get on to new things all that much sooner. Um, why do people give courses? Why are you doing this, Rajesh? I mean, we're all doing it for the same reason.
Right.
We're all doing it because we want we want other people to have the best opportunities.
Right.
And if we can give them a hand up, we want to give them a hand up. And there's really nothing more to it than that. I mean, financially, it's not a smart move. It detracts from your professional uh, time. When you're doing these things, you're not writing research papers or something. But it comes back to being part of the community, as opposed to, if you just want to do research, get yourself a server and find a cave
Mhm.
and isolate yourself and do that.
Right.
But I think we do better when we're in a community, and part of being in a community means helping those who have gone before you when they need help, and helping those who have come after you.
That's awesome. Okay, so I think that's great advice. So let's get back into the lesson for today, and I will mute my mic and let you share your screen.
Okay.
All right.
So I know that everyone, I know that this is a little bit different than how these things normally go, and that's my fault. I misunderstood how how this session was going to go from the very beginning. So when Rajesh and I first talked about this, I said, "Oh, okay, I'll make some slides and I'll make a notebook," and I did all that stuff, and then I realized, oh, all right, but here we are, so let's do it. So um, I am StreamYard is now telling me that it won't allow me to do it. Let's try it again. Tell you what, let's here we are. Ah, did that work? Anybody? Are you seeing my screen? Okay, it looks like you are. Rajesh, can you tell me, is it working okay? Oh, maybe when I'm sharing, I can't hear anyone.
No, it's working great. So I
Oh,
think
good.
mute
Okay,
it.
great.
It's good.
Okay, so let's talk about this stuff real quickly, and then we'll look at the notebook. So reinforcement learning, what's this all about? So you guys have seen all this stuff on supervised learning and unsupervised learning, where we have data and we have labels, and we say we know what we want the machine to learn. How about those situations where we don't know what we want the machine to learn? We just want it to learn to do it. Like I have a robot and I want it to walk. I don't know what's the best way to get that robot to walk. Hey, robot, you figure it out. That's reinforcement learning. So here's an example I like to use: elevators. So you have a big office building and you have a bunch of elevators and they move up and down. How do you control them? Where do they wait? Suppose it's the middle of the morning. Where should all the elevators go? Should they go to the top in case people want to go down to lunch? Should they go down to the bottom to wait for people who are coming in? Should they be staggered? Should they be in the middle? I don't know. And in fact, it changes from day to day based on the weather and who's in the building and who's visiting. So we don't know the answer. We don't know how we want the computer to control the elevators. What we can say is if it's doing a good job or not. So for example, we can look at how long people are waiting. And if they're waiting a long time, we can say that whatever you're doing, it's not so good. And as the wait time goes down, we can say, oh, whatever you're doing, it's better. So this is like the children's game of hot and cold. So as you get closer to the answer, we say you're warmer, you're warmer. You get away from the answer, we say you're colder. And the answer can even be moving. And we just keep telling you when you're hotter and colder, and the computer keeps adjusting itself to become hotter. That's reinforcement learning in a nutshell. So let's look at how this happens. We typically think of reinforcement learning in terms of an agent and an environment. So the easiest way to talk about this is with a game. So here we have two characters playing a game of chess. So the first one to move is the mouse. So the mouse is the agent. And everything else in the universe is the environment. The board, the other player, the bird that's looking on from the sidelines, all of that is the environment. So the environment is just the catch-all term for everything that is not the agent. And the agent is the thing making decisions. So the mouse makes its move. Now the elephant is the agent, and everything else, including the mouse, is the environment. So the mouse makes its move, the elephant makes its move. Then the mouse becomes the agent again, the elephant becomes the agent again, and back and forth it goes. Who's the agent? Who's making the move? What is the environment? So we often think about it in sort of these terms. This is the flow. So let's imagine we're learning to play tic-tac-toe. The environment, or noughts and crosses, or X's and O's, it goes by different names. Basically, we have a 3x3 board with X's and O's, and we alternate moves, and we want to get 3 X's or 3 O's in a row, straight, horizontal, or diagonal. So the environment says, I am in control of the board, because the environment's in control of everything that is not the agent. And then it says to the agent, here is the board, and here are your options. Here are the things you can do. And so the agent looks at it and says, well, what am I going to do? I have a board. Maybe I have some history. I have things I've learned. I have information I've saved for myself. I'm not asking anyone else. It's all inside of me. And I look at my record.
Andrew, sorry to interrupt you. Your slides are not advancing.
My slides are not advancing. I'm very sorry about that. Are you
Yeah.
seeing it now?
Yes, we're seeing that now.
Very weird. Okay, well, this was the mouse and the elephant. If that made no sense at all, this is the mouse making a move. That's the elephant. This is the mouse. This is the elephant.
Excellent. Thank you.
Okay, so now we have the environment making a move, and the environment says, here's the board, and the agent says, well, I've got the board and I've got my moves. I will make this move. We're losing all of the animations because I'm stepping through them, but you get the idea. The agent says, I'm going to make this move. I'm going to put in this red circle. And now the agent is done. Now it goes back to the environment, and the agent does not actually make the move. And this is very important. The agent says, this is the move I intend to make. So think about this in terms of the elevator scenario. The agent, who is the scheduler, might say, move the elevator to the 30th floor. But as the elevator is moving, someone in between pushes the button, and so the elevator has to stop. So the environment applies the move to the rest of the world. So in this case, the agent says, I want to go here. And so the environment says, okay, fine, I will make that mark. And now I come up with, remember this hot and cold story I gave you? We do it with numbers. And it says, the hotter you are, the better the move you made, the higher in number you'll get. Typically, the number is between 0 and 1. We just do that for convenience. And so the bigger the number, here, 0.7. That means that was a pretty good move. Maybe not victory, but not bad. And so that goes back to the agent. That's called the reward. So all the agent does is it gets the current state of the world and what it can do. The agent chooses something to do and says to the environment, go do that. And then the environment says back to the agent, here's how well I score what you did. That's a reward and that's a number. So let's actually see this in action. So I'm going to stop sharing, and now I'm going to share the notebook. And I am not. Sorry, everyone. We're just working out how to share screens here. Share screen, share screen. It makes me go through all these steps. It says your browser has blocked your screen. Well, that's lovely. Let's try that again. Share screen. Sorry, everyone. We did test this. Share the screen. Your browser has blocked your screen. Click the screen icon in your address bar. Sorry, everyone. It's giving us. It's not letting me do it. It just did, right? Everyone saw my screen a moment ago. So it's broken itself. It's not letting me do it. Rajesh, it's not letting me share the screen. Can you bring up the notebook and I'll just ask you to scroll through it? I can't hear anyone.
Yeah.
Can anyone bring up? I see your lips moving, but I can't hear you. Can you bring up the notebook and then I'll just tell you what to do, I guess. It's not as nice, but we don't want everyone sitting around while we debug whatever's going on here. Let me try it one more time.
Okay.
And if it doesn't work, no, it just keeps blocking me. All right, so hi everyone. So what we're gonna do? Oh, I'm sorry. I was gonna bring up a whiteboard and I was gonna draw pictures, and we've been befuddled by technology. I'm really sorry. I had my tablet ready and everything. So I'll here we have visual aids. We're gonna play a game called NIM. Now there's lots of versions of NIM and they go by different names, but here's the simplest version of NIM. We start with a pile of sticks. This is too many sticks. We start with a pile of sticks. We have two players, player A and player B. On each move, a player must take 1, 2, or 3 sticks. Those are your only options, 1, 2, or 3. So each player can see how many sticks there are. There's no secret. You can count them. So player 1, let's say player 1 is on this side. Player 1 randomly says, I'll take 1 stick. Okay. Player 2 over here says, I'll take 2 sticks randomly. This player 1 says, well, I'll take 2 sticks. Now, what is the goal of the game? The goal of the game is to not take the last stick. Never take the last stick. The last stick is on fire. You don't want it. So whoever player this is now, I've lost track, looks at the 3 sticks and says, I don't want to take the last stick, but I must take 1, 2, or 3 sticks. I definitely don't want to take 3 because then I have the last stick. So maybe I'll take 1. Now the other player looks at it and says, well, I don't want to take the last stick. I'll take 1. And now whoever's player turn it is now loses because there's 1 stick left and they have to take it. A better move back when there were 3 sticks was for that player to say, I'll take 2, leaving the other player with just 1. So we're going to learn how to play this game. Now, a lot of you are probably already ahead of me. You've probably gone, well, wait, there's a strategy for this. Yes, there is, but we deliberately picked a simple game. So if we could scroll down to the next cell, we're just going to bring in NumPy, and we're going to scroll over this stuff because, this is just bringing in the graphics things. Here's how we're going to control the world. Our smallest pile will have at least 4 sticks. That way nobody loses right away. If you start the pile with 1 stick, you lose. So you always have 4 sticks. I said the largest pile is 60. We'll see. Once it gets big, it doesn't matter how big it is. It doesn't change your strategy. And then we're going to draw plots of playing multiple games. And so I said, well, we'll play 500 games. That's a good thing. So let's scroll down to the next cell. We don't actually need, and Rajesh, can you go up to runtime and execute all the cells so that we have all the graphics waiting for us when we reach them? Yeah, go to runtime and run all. Perfect. So while that's happening, so if you can scroll down, so it's it's doing it all, and it'll catch up with us in a moment. So I'm not going to walk through all this code. You've got it and you can read it. Basically, all it does is it alternates two players. One player takes 1, 2, or 3. The other one takes 1, 2, or 3. The next one takes 1, 2, or 3. And whoever ends up with the last stick is the loser. So let's play lots of rounds. So here in cell 4, we're just going to run this for 100 or 400 times or 500 times. We're going to add up who won each time, or we're going to keep a record 1, 0, 1, 0, 1, 0, depending on whether player 1 or player 2 won. And now we'll plot the running average. Now, since the players are playing absolutely randomly, we expect that, player 1, let's say player 1 is the agent. We expect player 1 will win about half the time. And sure enough, there, we ran it 500 games and player 1 won roughly half the time. And if we let it go longer, it would probably oscillate around this 50% mark. So great. So that's what happens if you play randomly. But let's not do that. Of course, let's learn to play. So scroll down, please. Scroll down to the next cell. So we're going to begin the next cell of code, please. Right. Just keep going. You guys can read all this. I'm going to create an environment. It'll be a class, and the environment just starts itself up. So we'll have two things that we really care about, a computer player and the agent player. And those will be routines. And so Python being Python, we can just pass them in. So the environment, I'm sorry, if you can show us the whole environment cell. So it only knows how to do a few things. It knows how to start itself. To start a new game, it just sets the pile size to a random value and zeroes out the move list. We can ask for the pile size. We can print out the pile size. Scroll up, please. And then the next important things are that we can apply the moves. So when the agent says, I have a move, I'm going to take one stick. What this thing does is it just says, okay, take that stick out of the pile. Remember that the agent took one, and then see if the game is over. And when it's time for the computer's move, we do the same thing. It's just the environment calls the computer. So here we're not alternating. One piece of code is the agent the whole time through, and the agent is playing the environment. So we're not doing that back and forth the way we did before. It's always the mouse, always making a move, and the elephant is part of the environment, always doing the response. It's like playing a solo game. So let's see how this might work. So scroll down. And again, I'm going over this quickly because you guys have the code, and I don't want to get lost in the Python noise. I want to talk about the big ideas. So this is going to be our loop, and it's got a lot of print statements, which makes it look a lot longer than it is. All it does is it says, agent, make a move, and then apply the move and see if the game is over. If not, environment, you make a move, see if the game is over. If not, back to the agent. That's it. And then there's just a bunch of print statements in there because we'll see them later. It's nice to keep track of what's going on, how big the pile is, how many sticks each player took. So scroll on down. Let's take a look at a naive computer player. So it initializes itself. It does a new game. Those don't even do anything. There's no code. And its move is pick a random number between 1, 2, or 3. And this is Python for 1, 2, or 3. Basically, it's starting at 1 and ending before 4. And that's 1, 2, 3. So he says, I'm going to pick 1, 2, or 3 sticks. I'm going to make sure I'm not asking for more sticks than there are in the pile. So if the pile has 2 sticks and I pick 3, we make it 2. And that's it. That's all it does. It picks randomly. So let's look at the agent. The agent will be the same thing. The agent will also pick randomly. The agent has one more routine here called process the reward. It gets back the reward from the environment and the new pile size. And we'll see why that's useful to have later. Right now, that doesn't do anything. So now we have these two random things playing each other. And if we scroll down, there's just some little plotting routines. Scroll past those. Scroll down to the next graph. And we'll see that if we have two random players playing each other, we expect the results to be where the agent wins about half the time. Here we are running one round, and you can see I've set verbose equals true. So we get to see we're starting with 8. The agent took 1. The computer took 2. The agent and so back and forth. We get to see the back and forth. So now let's play a whole lot of games, but we'll turn verbose off. We'll just leave it to the default of false. So here we are, and scroll down to look at the graph. And sure enough, the agent wins about half the time. which is exactly what we'd expect. So this is no different than that code we saw at the beginning, but now we have this nice structure, right? We have an environment, we have a computer, we have an agent, and now we can make things more interesting. In fact, we're not going to change the environment at all anymore, and we're not going to change the loop that says computer plays, agent plays, computer plays, agent plays. All we're going to do is improve the agent and the computer. So let's make a smarter agent. So scroll past all the, we're talking about all the stuff here. What I'm going to do is I'm going to tell the agent to remember the moves it has made. And that way, when the game is over, if it wins, it can make a table. And it can say for every row in the table says, again, I wish I had my screen sharing on. I'd be drawing you pictures here. So I'm going to wave my hands. So we have a table, and each row in the table corresponds to a certain number of sticks. And each column is how many sticks we picked up. So there's only 3 columns because we only have 3 legal moves, 1, 2, or 3. So the first row is I have 1 stick. So I can only make 1 move. So let's suppose we're down here at the where we have 5 sticks. So we have 3 choices of move. And if we were to play each one of those 3 moves, we would end up winning or losing. And so we would have 3 cells. And we will mark the reward we got. So we know if a given move leads to success or not, because we'll remember it. So we'll remember the moves that worked in this table, where the rows correspond to how many sticks there are. That's the state. And the columns correspond to how many sticks we take. That's our move. So now for any future time we get back a pile of a certain number of sticks, we can look at that row in the table and we can say, have I ever played that many sticks before? And if so, what was my reward? Did 1 stick do well? Did 2 sticks do well? Did 3 sticks do well? And whoever did the best, I'll use that one. I'll play that one again. That's called a Q table. Q stands for quality. Really, we're remembering the quality of our move. So that's all we're doing. We're going to pick a random number and we're going to save it. And then later, I'm sorry, if all the entries are the same, if they're all 0 at the beginning of the game, we pick a random one. Otherwise, we pick the largest one. And then we just play it like before. So let's scroll down and let's see how well this strategy works. And here we're going to remember that this is the part where we actually store it in the table. The very last line, self.q table, pile size, so indexed by the pile size, and the action, we just pop in the reward. So let's play this strategy. So we'll remember here we are playing one game and we watch all this stuff happen. Okay, it's all working properly. So let's scroll down to the graph and see how well we do. Whoa! Remembering our moves in the Q table means that we are doing fantastically. We're winning 93% of our games. And if we let it go longer, it would probably work its way up to, maybe total success all the time. Now, we'll see later, it's probably never going to get to total success, but still, fantastic, right? Well, not really, because the computer is playing randomly. There's no thrill in playing against a really bad opponent. So let's make the opponent smart. So here's the Q table that it learned. And I've flipped it on its side because it fits better on the screen that way. So each row is 1, 2, or 3. That's how many sticks did we pick up. And each column is how many sticks were in the pile. And we can see there's really only 2 values in here. There's blue when we lost the game and pink where we won the game. So there doesn't really seem to be much of a pattern here. And that's because the computer is playing randomly. So, whatever we do, we can't really be sure it's such a good idea because we don't know what the computer is going to do next. So let's make the computer smarter. So what's the best way to make the computer smart? Well, that's to figure out the strategy for winning. And there is a strategy, and I invite you to think it through. But as you can see here in the middle of the screen, how to win, always leave the player with 1 + 4 n sticks, where n is an integer. And I'll leave it to you to think about why that's the strategy. But anytime you have a pile, you want to take the number of sticks that leaves the other player with 1 + 4n. You will always win if you can do that. Of course, if you're faced with 1 + 4n sticks, you lose unless the other player makes a mistake. So, okay, let's I have about 5 minutes, so let's look at what happens. So we're going to implement this. It just takes one line of code. It's the first line under make move. So now we have our learning agent that keeps a record in the table and our genius opponent. Now the computer will play a perfect game whenever it possibly can. Let's see how we did. Scroll on down to the graph. Well, okay, that's pretty much what we'd expect, right? The computer is perfect and we are doing awful. We're winning 15% of the games. We are terrible. Well, of course we're terrible. We're playing against a perfect opponent and we have no strategy. We're making random moves and we're playing the same random move again. But the really interesting thing here is that the trend is going up. We are learning. Even it's very slow, but we are learning. What are we learning? Well, that will be revealed by the Q table. Scroll down a little bit. Look at that. There seems to be a pattern here. The pattern is the 1 + 4n pattern. The system is learning when I play a move that leaves the other guy with 1 + 4n. Of course, it's not thinking about it that way. It's just recording the moves that win. But the moves that win are the one that leaves the opponent with, 5 moves. So, for example, let's look at 8. So, how many sticks does it take? It takes 3 sticks because that leaves the opponent with 5. 1 + 4. So it's learning how to play, but it's doing terribly. Well, what's going wrong? Nothing's going wrong. We just have to play longer. So the problem is if we take this strategy with this, sort of blind search and we just let it play longer, that's fine. But one, we have to let it play for a very long time. And 2, it's learning very slowly. So we're burning up an enormous amount of resources. We're getting there, but we're getting there so slowly. So can we do it any more efficiently? And the answer is yes. We can make a better agent. We can add a few things to our strategy. And I'm not going to go into those. They're all right here. And so if you read this section on making a better agent, you will see how to speed up the strategy. So let's scroll past this. Under this text, we have an implementation of the smarter agent. Here it is. Now this is implementing all of those 3 improvements. So let's move down and see how well that works. So go down to the graph, please. And you've got all these. So again, you can read this stuff over and see exactly what it's doing. So in 500 games, we won 13%, but we're doing better. We are learning. If we scroll down again, okay, and here's the heat map. And you can see the heat map is coming in perfectly. So our strategy is working well. We are learning exactly what we need to learn. And we actually are learning it more efficiently than before. So scroll down because we want to see what happens if we keep training. So here, instead of 500 runs, we have 20,000 runs. And if you scroll down a little bit so we can see the whole thing, you can see we're doing great. We have learned and we're now winning about 2/3 of the time. And if you scroll down, you can look at the heat map. Look at that. It has learned how to make the right move every single time it can. So why is it only winning 2/3 of the time? Well, it's going to lose sometimes because the agent always goes first. So the pile starts out with a random size. If the pile starts out with 1 + 4n sticks, then the player has to lose because the computer knows the perfect move to make. So the computer always makes the perfect move and you have to lose. You can never do better than 3/4. But why isn't it doing 3/4? Why isn't it at 75%? Well, that's because one of our 3 strategies was called explore versus exploit. It says when I look at the table and I look at the 3 numbers there, normally I pick the biggest one because that's the one that got the biggest reward. But maybe I haven't searched the others. Maybe those are still 0. Maybe if I try one of those, I win the game even sooner or better. So explore says, pick one of the moves you haven't tried before. Exploit says, pick the move you know is best. And that's a trade-off. And you can set a little knob. There's a number in the, in the text and actually in the code, there's a little number you can set. And you can say, how often do you want to explore rather than exploit? So I crank that number up to maximum, scroll down, and sure enough, we're winning about almost 75% of the time. If we played a little bit longer, we would be up to 75%. And if you scroll down, I think that there's one more graph. Right, there's the heat table we learn. And it's perfect. And then we have some discussion. So if you scroll up, we'll leave you at the heat. We'll leave you at the Q table. This is the perfect Q table. Now there is a problem here, which is that the Q table grows in size. Right, the bigger the board, the more moves there are, and even for a pretty big game. Actually, if you scroll down, that way I can give you the right numbers. You can see in the discussion. So yes, so if we were playing tic-tac-toe on a 15 by 15 board, the Q table would need 10 to the 82 cells. So that table needs more cells than there are atoms in the visible universe. And we're not even storing the data. That's just how many cells we need. So it's actually like 1 billion universes. So that doesn't work. So the way we get out of this dilemma is we use the other deep learning techniques that you've seen. And we write a neural network that learns the Q table. So instead of storing the Q table explicitly, we have a neural network that says, give me an input, which is the number of sticks and the number of and the number of options, 1, 2, or 3 options. So really it just says, give me the number of sticks. And rather than consult a table, I will consult this neural network that has learned the table, and I will tell you how many sticks. And that way we don't have to store the whole table. And that's how DeepMind, or that's one of the key components behind how DeepMind wrote AlphaGo and AlphaZero, which is arguably the best player of the game Go that's ever existed in the universe that we know of. So that's reinforcement learning. We have an agent and in an environment. And the agent says, tell me what my options are. I'll choose somehow, and I'll keep some private information. It's called my policy. I'll keep this private information that tells me how to pick, and I can consult what I've done in the past. But ultimately I say, here's what I want you to do. The environment does it and says, here's your reward. You did well, here's a cookie, or you did badly, no cookie for you. Instead of just giving you a cookie or not, we give you a number between 0 and 1. The bigger the number, the bigger the cookie. And so over time, you remember the moves, the steps that got you cookies. And those steps could lead you to more efficiently scheduling elevators, working out how to, do the logistics for a fleet of 20,000 delivery trucks, any problem for which, teaching a robot to walk, any problem for which you don't know the answer. All you have to do is set up one of these systems, build an agent, give it a good policy, and let it know when it's doing well. And it will wander around until it finds something that gives it good results. And then it will follow those results and make them better and better and better, just as we saw with the Q table. You back up, if you can scroll up just that Q table, please. Rajesh, if you can scroll up one cell, perfect. That's the goal. And it will learn that, because that's what we're reinforcing. And that's what I have to say. Thank you, everyone.
That was fantastic. Thank you, Andrew. And any questions so far on any of the material that Andrew taught, or anything in general? Please feel free to post them in the comments.
Yeah, if there are questions, I'm happy to answer. I'm not sure how to see comments. Here we are. Yeah, sorry about the screen share stuff, guys.
No worries. I think I had my whole computer crash a couple of times.
No. Welcome back.
Not today, but in the past.
Oh, I see. Okay.
All right. So thank you again so much for being with us and sharing your time with us and expertise. This is truly has been an honor. Thank you.
Oh, it's been a great pleasure, and thank you so much for giving me this opportunity. I'm humbled to be able to contribute to this wonderful class you've prepared. Thank you.
Awesome. All right, so let's go back to our class, and then I wanted to wrap up with some thoughts in the end. So that was Andrew. It was a fantastic lecture, and as he said, essentially in reinforcement learning, you have an environment, states, actions, rewards, and then your goal is to maximize the total reward. And then you do that through figuring out the policy for choosing the next action based on the rewards you have accumulated so far. As you said, like if the Q table becomes too large, then you start training it with other deep learning methods that we covered in the previous classes. So this brings us towards the end of the course, and I want to thank the guests who have given us the time and their expertise. And I think it's amazing that all the schedules lined up in a nice way that I was able to get time from them. So that was pretty awesome that we were able to learn from all these experts in different areas and enhance our learning. Also, thank you to ACM SIGGRAPH for making this class possible. And there's a lot of prep work that goes behind each of these classes. So 7 hours of me prepping and teaching with all behind the scenes work that Tomas has done to get this program approved with SIGGRAPH, Alex and Tim and the student volunteers who are managing the stream and posting the questions for us to answer. So this has been a great experience, and thank you to them all. So I wanted to summarize what we learned through the course. So we covered a lot of things. And if you take away anything from this course, are these next two slides. So one was the summary of what we covered was basic data analysis and plotting, regression. We learned about the universal approximation theorem, that anything can be approximated with a simple neural network that is fully connected, provided you have enough data and enough time and resources. But yet there is no free lunch. A network that can solve for a specific problem cannot be generalized to solve other kinds of problems. So based on the distribution of the data that you get, that is how your predictions are limited to that kind of distribution. We looked at the fully connected networks, the simple ones, and then the final layer, you could have a number that you can predict, or you can have classes that you can predict for classification. We learned about CNNs as the building block for image-based training. We talked a little bit about recurrent neural network, and we built a whole translation system which tried to predict the next words from a Shakespeare-like style. We didn't talk about UNet in detail, but it's kind of like CNN. It makes it better for detail transfer because you reconnect parts of it to feed back into the network as a whole. We saw the variational autoencoder, which tried to approximate the given distribution as a Gaussian distribution with mean and variance. So you can then start creating new kinds of images that you get in. We did some transfer learning with multitasking CNN and FaceNet to do facial recognition. That worked pretty well. So that was like a simple setup, but it did a whole lot to kind of let us put an end-to-end system that recognized images and then identified them using a second network, FaceNet with the triplet loss. We looked a little bit at the GANs to do some more generative images. And the GANs are variational autoencoders. They are doing similar things, but in a slightly different way. So GANs are essentially sampling the distribution in a direct way where you take the noise as an image and then try to kind of push it into the direction of the distribution so you get a sample from the distribution directly. And today we covered reinforcement learning, which Andrew talked about in detail, and we'll leave you with that notebook that you can play with more. So that's the content of the course today. And in terms of the theory, I think a lot of people ask me about, like, where can I learn the math and what is happening actually in the neural networks and machine learning in general. So this slide is kind of summarizes the entire thing into few sentences. There are some terms you can look up and learn more. But essentially, you have some data that you have, and they come from some unknown distribution that you don't know about. The house prices or images of cats or images of dogs or just general images, they all belong to some distribution you don't know about. And what we are trying to do is we are trying to take a known distribution, something called P here, which also known as posterior, and then make it so that it's as close to the unknown distribution as possible. And once you get there, then you can sample from this known distribution instead, because the unknown is unknown, so you can't sample from it. But you can sample from this known distribution, which is as close to the unknown one as possible. And that's all there is. I think that's like the majority of the math that happens behind the scenes, or the theory of AI and machine learning, and that's exactly what we're doing. And some of these techniques were like invented 300 years ago using Bayesian inference, where you have a given distribution and which is a posterior, and you have some information about the unknown distribution, and you get additional information using the data that you have. Then you can apply this Bayesian theorem or formula to kind of get at the new sample. So when we do regression, we essentially just take the log of the posterior distribution, and that gives you the squared error. And we saw how they were equivalent. When you do the classification, you take the softmax of the logs, and each of those log values give you the probability. And that's essentially the cross entropy that we found. And then the variational autoencoder is creating a Gaussian distribution that is as close to the unknown distribution. And GAN, in a sense, tries to directly sample from the unknown distribution by pushing this noise, initial noise, into the direction of the distribution. So if you need to learn any more theory, just look up these terms, and I think that's what will give you the math. And the rest of it is tensors and matrix multiplications and process and tools that you have in TensorFlow. So when you connect this theory to the tools, you can then start doing all these things. So go read about these things if you want to learn more. And for the practice part, we introduce a bunch of vocabulary, and sometimes it can get a little bit too much. But then if you kind of just practice it enough times, you will get used to kind of saying these words like bias, variance, overtraining, hyperparameters, and all these things. As you get more familiar with it, they become a little bit more understandable, and then you can start tweaking them and trying to figure out what they mean. And just understand that you need lots of data. You can augment it. You can create synthetic data. You want to have your data be unbiased, so you're not taking in the bias from the data and then putting that into your predictions. You want to fight against bias and variance. And you want to find a sweet spot where you're not neither overtraining nor undertraining. And then you tweak the hyperparameters until you get to the loss shape that you need. As long as it's going down and flattening out towards the end, you're in a good space. And then work like a scientist. Like as Andrew emphasized, like you want to hypothesize something, you want to do your experiment, observe it, record changes, and repeat. So keep doing this loop of trying things out. And there's a lot of things we didn't cover. It's a big, vast field. So we didn't cover cloud-based techniques because as the data gets bigger, as the model gets bigger, your home machine is not capable of doing these things even the cloud machine that you're getting from Colab, it's a small machine. So you want to actually then pay for machines on the cloud and do training and deployment. There's a whole emerging field of MLOps, kind of like DevOps, but people who orchestrate these things, they farm it out to as many processors and machines as possible. So there's something to learn here. So the jobs are not only in like research and coming up with new models, but also in understanding the data processing, engineering side of things, where you have PyTorch or TensorFlow, and this MLOps side, where you are trying to figure out how to do this as efficiently as possible among multiple computers in the cloud. We didn't talk about logging and visualization of we had simple matplotlib-based graphs, but there are tools there called TensorBoard and similar tools that companies provide that you can do checkpointing for training that goes on for weeks. You may want to checkpoint, and so that when the machine crashes or something bad happens, you still have your data, still have the checkpoints, and you don't have to start again from scratch. You also want to, from time to time, do intermediate layer visualization to see how things are going on. And there are other methods other than neural network that also work well on training things, like random forest and XGBoost. And then there's other theory that we skipped because we wanted to keep it simple and understandable. So now that we have all this, where do you go from here? One thing I can give you from this, you can start running these things on your machine, because sometimes the cloud machine can go away and it can be put in bad state. So you can start programming it. If you have a Mac or a Linux system, you can use this use simple method called pip freeze, and it will give you whatever was installed in that virtual Colab machine. So once you have those requirements, you can create your own Python virtual environment in your computer locally, and you can then install it, all the software that you need using the pip install. And then from there on, you can just run things on your local machine. What else can you do? You can read more. This is a great book, deep learning book, that has lots of theory, and there's all the lectures from the book are also available online. Andrew has a new book about teaching deep learning, but more visually. So for me, this is great because I'm like a very visual person, and I like images and pictures more than formulas and math. So this is a great book if you want to get a better understanding of how things are working. You can learn more statistics, and there is a GitHub page of a lot of the deep learning papers, but they're categorized in a way where it goes progressively from easier to harder, and there's even more comprehensive list of resources. So one of the best videos online is from this 3 Blue 1 Brown. They make excellent videos, tutorials on a variety of different topics. So if you're looking for more videos to see and understand, go follow those. And that's about it. So I would like us to stay connected. If you have questions, if you do other projects, and if you need help, please feel free to link with me on LinkedIn or chat with me on Twitter. And at this time, I will take any last questions you might have. So I think there are lots of possibilities in VFX and animation for applying machine learning. And a lot of this research is still fresh and new. So it means like it takes a lot of resources and tweaking to get it right. But the advantage that some of the larger studios have is that we have a lot of data. We have data from past films. We produce like 100,000 frames per film, so we can train It's a matter of getting the time and the resources to do and to do it right. But the possibilities are like endless. I think just the application of denoising lets us render things to a certain SPP, and then we can apply denoising. So that already saves us a lot of time. So I would like to kind of pursue some more work in the areas of trying to make the creative things better, or to help the animators or lighters. So there's like anything that you do which comes out as like you do a rough version first and then you refine it, which is pretty much every part of the pipeline in VFX, then you can learn and train it. So at some point, you can then go from rough storyboard to final frame. Can you do that? So that's kind of like a holy grail. So if you have early storyboards, can you come up with the final frame? And if you can do that, you can make movies with a computer. All right, so we are a little bit overboard, but because it's the last class, I think it's okay. So thank you again for following along in this journey with me. And any questions, again, just connect with me. And thank you again to all the SIGGRAPH volunteers and Thomas. Goodbye, everyone.
At SIGGRAPH 2020, more than 10,000 individuals from 95 countries gathered virtually to experience over 350 hours of content presented by more than 1,600 contributors. What resulted was pure SIGGRAPH. Robotic advances use subtractive fabrication techniques to carve foam and similar materials like an artist. Modeling and predictive computation creates a more robust and accurate time-stepping of nonlinear elastodynamics. New investigation into damage simulation could change the landscape of video and game effects, as well as surgical training. Novel healthcare technologies point toward new ways to transform and enhance lives. Research will help users to create reprogrammable multicolor textures made from a single material. AI-driven technology pushes the capabilities of crowd simulation. Award-winning animation showcases the latest in computer graphics. Real-time and gaming technology advancements transform interactive storytelling techniques and explore new applications of the technology. Evocative digital artwork uses machine learning to create visceral experiences. Now is the time to share your research, your innovations, and your creative inspiration. SIGGRAPH is your community, and we hope you'll share your work with SIGGRAPH 2021.